Welcome. Let's talk about the numerical method running in Python. So, running such methods such as graphical method, bisection, incremental, regular fallacy method, mm, Newton-Raphson, and second method. Um, let's talk about first the graphical method. Graphical method is a visual approach to root finding. You plot the function over a specific interval and observe where it intersects the x-axis. While it doesn't compute a root numerically, it's great for estimating root locations and intervals for other methods like bisection or regular fallacy. Now, here, in one graphical method, let's talk about it step by step. First step, retrieving the function. The function string is retrieved from GUI. Solve that graph underscore fx.get. Simplify parses the string into simpy expression. Lambify converts into numpy compatible Python function. Step 2. Get the plotting range. Lower and upper bounds are retrieved from the GUI inputs. If xl greater than or equal xu, it shows an error. Step 3. Plot function. Self that plot function is called when the parse function and the interval. This method handles generating the mat mat matplotlib plot with axis and grid. So why is it useful? Gives you a big picture view of your function behavior. Helps you uh, visually identify approximate root location or intervals where f of x changes sign. So now let's proceed to incremental search method. Incremental search method checks a function's value or regular intervals starting from given point moving by by a fixed increment. It finds a subinterval where the function changes sign, meaning a root likely exists in the interval. So here in run incremental, let's talk about it step by step. Input parsing reads the function as string from the GUI, converts it to mathematical function using simplify and lambdify. Step 2. Initialize parameters x0 that the starting point, delta the increment size, enter number of iterations. Step 3. Loop through increments. If for each iteration it computes x1 equals to x0 plus delta. If of x0 and f of x1 if f of x0 multiply if f of x1 is greater than or if less than 0, a sign change occurred indicating root lies between x0 and x1, and it break the loop when that condition is satisfied. Record result. Step 4. Record results. The data is stored for each iteration and shown in GUI table. Now let's proceed to bisection. Bisection method narrows down a root by repeatedly halving an interval where the function changes sign. It guaranteed to converge if the function is continuous. If continuous. Now, let's proceed to the code. Run bisection method. Here, the run bisection. Let's talk about it step by step. Step 1. Input parsing. Get function and interval xl and xu. Validate that f of xl multiplied by f of xu is less than 0. 2. Main loop. Calculate the midpoint xr equals to xl plus xu over 2 and evaluate if f of xr compute error. Check stopping conditions. F of xr equals to 0 or means exact root. If error greater than tolerance or approximate root. Step 3. Update bounds. If of xl multiplied by f of xr is less than 0, root is in xl or xr. Else, root is in xr or xu. Step 4. Store and display the results. Now, let's proceed to regular falsi or the false position method. Like bisection, but instead of using the midpoint, regular falsi finds a better estimate by linear interpolation between the endpoints. It uses the second line between the points xl and f of xl. Now, let's proceed to run regular falsi. Now, let's talk about it step by step. How it works. Step 1. Initialization. Get the function bounds, tolerance, and max iteration. Validates initial sign of f of xl and f of xu. Interpolation formula. Compute xr as xr equals to xu minus f of xu multiplied by xl minus xu over f of xl minus f of xu. This is the x-intercept of the second line. Step 3. Update logic. Evaluates f of xr. Check it if 0 or error below tolerance. And update bounds accordingly like in bisection. Step 4 is the output. Display all iteration in a table. Now, let's talk about the Newton-Raphson method. An iterative method that uses both the function and its derivative. Starting from an initial guess x0, it updates using xn plus 1 equals xn minus f of xn over f prime xn. Now let's go to the run Newton-Raphson. Let's talk about it step by step, how it works. parse function and derivative. Simplify parses function. Diff gets symbolic derivative. Lambdify turns both to callable function. Step 2, iterative update. Evaluate function and derivative at current guess x0. Update using Newton's formula. Stop if function is zero or error is below tolerance. Step 3, error check. If derivative is zero, it will error division by zero. Step 4, display its iteration result. Function value derivative next guess error. Now, let's proceed to the last method, which is the second method. Similar to Newton, second method, similar to Newton-Raphson but avoids derivative calculation, uses two initial guesses and approximates derivative by finite difference. Formula is xn plus 1 equals to xn minus f of xn multiplied by xn minus xn minus 1 over f of xn minus fxn minus 1. Now let's proceed to the code, the run second. Let's talk about it step by step. Step 1, initialization. Read initial guesses x0 and x1. Step 2, iteration loop. Evaluate function of both points. Compute next guesses using second formula. Measure error as x2 minus x1. Step 3, convergence check. If error below tolerance or function value is error, cause it will stop, and update x0 equals to x1 or x1 equals to x2 and continue. That would be the the explanation, and let's go to the exact how it works. Let me show you. Go, boys. Go, boys.